let's start where we left off. Last time we talked about three different ways of saying the same thing, three different equivalent axioms. So one of them was infinite descent. The other axiom we saw was well ordering. And then we saw induction or mathematical induction. And I showed that infinite descent implies well ordering, and well ordering implies induction. So to show that they're all equivalent, it's enough to show that induction implies infinite descent. But someone did this on Canvas, so I'm not going to do it. I'm going to do something else now. So I'm going to go like this. Let's see how we can do this. So let's say I have well ordering, and I want to prove infinite descent. And then I will do this one as well, proving well ordering using induction. Okay. So if I have well ordering, what does that mean? That means that I can assume every non-empty subset of natural numbers has the smallest element. It has a minimum element. And infinite descent, what I want to prove is that I cannot have an infinite sequence of numbers that is always decreasing. Okay. So let's do this. Let's say I want to prove 3. And let's say I take some infinite sequence of numbers. So I say, let's A be an infinite sequence of numbers. And when I say numbers, of course, I mean natural numbers at this point. Okay. I can look at the set of all the numbers that appear in A. Okay. So what is this A? A is basically a sequence. It's something like A0, A1, A2, so on, and it goes on forever. Right. So I'm going to define a new set. Let's call this set B. And I say this set B is all the numbers, so all the numbers X, such that X appears somewhere in my sequence A, such that there exists some index I where AI is equal to X. So the only difference is that A is a sequence. I have an order on my numbers. B is just the set of all the numbers that appear in A. Okay. Now, B is a non-empty set because A0 is in B, right? But I can assume well ordering here. So I know that B has a minimum element. B has the smallest element. Okay. So I say B has a minimum. Let's call that small b. Okay. But here's the thing. Small b is the minimum element of the set B. So there should be some index where AI is equal to the small b. That's just by the definition of the set B, right? All I'm saying is that, well, I had this set which has all the numbers that appear in A, and I'm looking at its minimum element. So this minimum element should also appear somewhere in A. Okay. So I know that there exists some I such that AI is equal to B. Okay. Now I say just look at the sequence A up until index I. So I have A0, A1, A2, so on. And at some point I have AI, which I know is the same as B. And then I have AI plus 1, AI plus 2, and so on. What can I say about AI and AI plus 1? Well, they can't be, right? Because AI is the smallest possible element. Right, so AI, yes. So AI plus 1 cannot be smaller than AI. So this means that I took any infinite sequence and I showed that it cannot always descend. Right, which is exactly what I wanted to prove. I wanted to prove the axiom of infinite descent, which says that it is impossible to have an infinite sequence of natural numbers that is always decreasing. And the way I proved it is that I took any sequence, any infinite sequence of natural numbers. I looked at this minimum element B, and I say, well, after this minimum element, it cannot decrease. Okay, great. So we went from well ordering to infinite descent. Now let's do this one. Let's try going from induction to well ordering. And again, I could go directly from induction to infinite descent, but just look at canvas. So this is 4. I have induction. I want to prove well ordering. And remember, again, well ordering is this property that any non-empty subset has a minimum element. Any non-empty subset of natural numbers has a minimum element. Okay, so let's do this like this. Let's say A is a non-empty subset of natural elements, of natural numbers. Okay. And let's try to do proof by contradiction. Let's suppose that A is a non-empty subset of N, and A does not have a minimum element. Okay. And does not have a minimum. Okay. So I'm just going to look at the set of all the natural numbers that are not in A. Okay. So let's just say I define B to be the complement of A. By the way, when I write something like this, it means that I'm defining something. So B is the complement of A. Okay. Now, I want to do induction on something. And remember that when I want to do induction, I want to have some property P. And I want to say that every natural number has this property P. Okay. So here's the property that I want to look at. So I define P of N like this. I say for every I that is less than or equal to N, I is in B. So P of 0 just says that 0 is in B. P of 1 says that 0 and 1 are in B. P of 10 says that all the numbers from 0 to 10 are in B. Okay. I want to prove this P of N using induction. Okay. So I want to say, let's prove that for every natural number N, P of N holds. And let's prove this using induction on N. Okay. I have to first check my base case. So does P of 0 hold? What is P of 0? P of 0 just says that for every I less than or equal to 0, I is in B, right? But the only I that is less than or equal to 0 is 0 itself. So P of 0 is simply just saying that 0 is in B. Okay. Now, why do I know that 0 is in B?
Because you can the induction, you know that 0 is smaller than
Yes. So if 0 is not in B, then 0 should be in A. But if 0 is in A, then 0 is the minimum element of A, but I was assuming that A doesn't have a minimum element. Okay, so 0 must be in B. So this case is done. This is the base case. Now let's do the induction step. What is my induction step? I want to assume P of N, and I want to prove P of N plus 1. Okay, so this is my induction step. Basically, assuming P of N, I want to prove P of N plus 1. So here's the thing. Again, remember what P of N was saying. P of N was this whole statement that for every I less than or equal to N, I is in B. So now I can assume it. So I can assume that for every I less than or equal to N, I is in B. And then using this assumption, I have to prove that for every I less than or equal to n plus 1, I is in B. Okay. But I already have most of what I want to prove as my assumption. Right. So for every I that is less than or equal to n, I already know that it's in B. So the only thing I have to prove is that n plus 1 is also in B. Right? So let's do that. Let's prove that n plus 1 is in B. I do this by contradiction. I say, suppose n plus 1 is not in B. What does this mean? This means that n plus 1 is in A. Okay, so then n plus 1 is in A. But what is my assumption? My assumption is that for every smaller element, for every I less than or equal to n, I was in B. So this means that n plus 1 is the smallest element of A. Right? But I was assuming that A doesn't have the smallest element. So this is a contradiction because n plus 1 is the minimum element of A. And this contradiction shows that n plus 1 has to be in B, because if I put n plus 1 into A, then it would be the minimum element, but A was not supposed to have a minimum. Okay, so n plus 1 is also in B. And again, I know by my assumption that for every I less than or equal to n, I was in B. So putting these two together, I can say that for every I less than or equal to n plus 1, I is in B. Okay. But so far, I haven't really proven anything. So far, I just started with this set A. I said A is a non-empty subset of n. It doesn't have a minimum. I created this set B, and then I proved something about B. I just proved that for every natural number n, for every I less than or equal to n, I is in B. Where's the contradiction? Yes. So the contradiction is this part. I'm saying that A is non-empty, right? But what did I just prove? I proved that every natural number is in B. Because look, what am I saying? I'm saying for every natural number n, let me just write this very formally. We proved that for every natural number n, and for every I that is less than or equal to n, I is in B. Okay. Now just plug n for I, because n is less than or equal to n. So basically, we proved that for every natural number n, n is in B. Right? So we have proven that B is the set of natural numbers, which means that we have proven that A is the empty set. And this contradicts our original assumption that A is a non-empty subset of A. Okay? And basically, this contradiction shows that whenever you have a non-empty subset, it does have a minimum element. So we proved 3 and 4. Again, instead of doing this, you could just directly go from induction to infinite descent. But this also works, so all of them are equivalent. Okay. Let's see. Let's now do some examples of induction. So we're going to actually solve some real problems now instead of just showing what are the different techniques that we could use. So let's do this. Let's look at the Fibonacci numbers. And the Fibonacci numbers are basically a sequence of numbers that we define like this. We say that F0 is 0, F1 is 1, and then for every n greater than or equal to 2, f of n is equal to f of n minus 1 plus f of n minus 2. Okay. So basically, I have this sequence. I have I and f of I. So let's do 0, 1, 2, 3, 4, 5, and so on. So F0 is 0, F1 is 1, and then every element is just the sum of the two previous elements. So F2 would be 1, F3 would be 2, F4 would be 3, F5 would be 5, and so on. 6 would be 8. Okay, so these are the Fibonacci numbers. We want to prove some things about the Fibonacci numbers. So this is our first problem for today. I want to look at the sum of the Fibonacci numbers. So let's say that I just look at F1 plus F2 all the way to Fn. And I want to say that this would be f of n plus 2 minus 1. So I want to say that for every n, F1 plus F2 all the way to Fn is equal to f of n plus 2 minus 1. Okay, prove this. And of course, I want you to prove it by induction. You might be able to prove it using a different method too, but let's just do it using induction. Does it actually hold, or do I need F0 there as well? So let's just check it for 1. F of 1 is f of 3 minus 1, yes. F of 2 plus f of 1, yeah, I think this is correct. So let's do the base case. And the base case that I'm going to try here is actually n equal to 1. I mean, I can do it also for n equal to 0, right? But then this side would be 0. And this side would be f of n plus 2, which is f of 2 minus 1, which is also 0. So it holds for 0 as well. Instead of just doing one base case, I can actually do several base cases. So I can say for n0, on this side I have 0, on this side I have 0, it holds. For n equal to 1, on this side I have f1, which is 1. On this side I have f of 3 minus 1, which is also 1. This one also holds. Maybe I can try for n equal to 2 as well. Let's do that. So for n equal to 2, on this side I have f1 plus f2, so I have 2. On this side I have f of 4 minus 1, which is also 2. Great. Now I could use any of these as my base case. I can just use n equal to 0 as my base case. It's fine. Okay. So now let's do our induction step. So we're going to assume that the property holds for n, and we're going to prove that it holds for n plus 1. Okay, so I'm going to assume that f1 plus f2 all the way to fn is equal to f of n plus 2 minus 1. What should I prove? I should prove that if I take the same sum, but I go all the way to f of n plus 1, so I take one more term. I want to say that this is f of n plus 3 minus 1. Okay. But this shouldn't be too hard, right? So I want to find this sum, and I already know the sum of the first n elements. So I just have one extra element, right? So I can write it like this. I can say f1 plus f2, so on to fn and fn plus 1 is equal to, I take this part, and I already know that this part is f of n plus 2 minus 1. So this is f of n plus 2 minus 1 plus f of n plus 1. Okay. But here's the thing. What is f of n plus 1 plus f of n plus 2? It's just f of n plus 3. So I just put these two together, this one and this one, and I get f of n plus 3 and the minus 1 stands. And this is exactly what I want to do. Let's make it a little bit harder. So this is the second problem I want you to consider. Let's say that this time I only look at the odd elements. So I look at F1, F3, so on. So I want to say that for every n, if I look at F1 plus F3 plus F5, so on, to f of 2n minus 1, this sum is equal to f of 2. So now I'm not summing up all the Fibonacci numbers, I'm only summing up the Fibonacci numbers that are at an odd place, at an odd index. Okay. Again, we're going to do the same thing as before. So let's do our base case. And let's say I start my base case with n equal to 1. So I would have that f of 1, which is 2n minus 1, should be equal to f of 2. And I just look at my table, and f of 1 is equal to f of 2. So I'm happy, my base case holds. Okay. Now, let's do the induction step. And this time I'm not going to write what the hypothesis is and what is it that I want to actually prove. I'm just going to directly write the proof. So this is what I have here. I'm going to have F1 plus F3, so on, plus F2n minus 1. I'm going to also have one extra element, which is F2n plus 1. Right. I want to find this sum. This is equal to, and now again, I look at this first part, and by induction hypothesis, I know that the first part is f of 2n, right? So this would be f of 2n plus f of 2n plus 1. But by definition, f of 2n plus f of 2n plus 1 is just f of 2n plus 2, which is exactly what I get. Let's go forward and let's prove some more things. Well, I can give you another example, but I'm not going to spend much time on this because it's basically the same idea again. I can sum up the even numbers. So I can say for every n, f2 plus f4, so on, to f2n is equal to f of 2n plus 1 minus 1. How would you prove this? Well, there are two ways that come to my mind, and the reason I'm showing this problem is to just talk about these two ways. So one way is to just do the exact same thing. Let's do an induction, let's write the base case, let's write the induction step, let's make sure that it holds. But here's the thing, if you look at the previous problems, I know how to find the sum of all the Fibonacci numbers until some point, right? And I also know how to find the sum of all the odd indexed Fibonacci numbers until some point. So I can just subtract this from the previous one, and it will give me the sum of all the even indexed Fibonacci numbers until some point. So I don't really need to do another induction for this. If you want to, you can do it, but okay. I want to go to a different problem. I want you to prove that any two consecutive Fibonacci numbers are relatively prime, which means that they don't share any prime factors. Okay, so I want you to prove that for every n, f of n and f of n plus 1 are relatively prime. And again, being relatively prime means that their greatest common divisor is 1. Also, again, as usual, in this course, we use a lot of things and we will come back and define them later. So at some point, we're going to talk a lot about greatest common divisor. But at this point, I'm just assuming that you know what greatest common divisor is. I'm assuming you know what prime is, what relatively prime is, and so on. So this is one of those cases where you can, again, prove this by induction. But I personally feel much nicer if I use one of the other equivalent ways of doing induction. So I would prefer to do this using bell ordering or using infinite descent. Okay. But because we've seen that all of these axioms are equivalent, of course, you can also do it using induction. So let me do it using bell ordering. So here's the thing. I say, let's look at the set of all the counterexamples. So let's look at the set of all n for which this does not hold. Okay. So here's what I'm going to do. I'm going to say let A be the set of all natural numbers such that GCD of Fn and Fn plus 1 is not 1. Okay. The set of all natural numbers where Fn and Fn plus 1 are not relatively prime. Now, what do I want to do? I want to prove that this set is empty. Because if I prove that this set is empty, I have proven that for every natural number n, Fn and Fn plus 1 are actually relatively prime. Right? So we want to prove A is empty. Let's do proof by contradiction. Let's say I assume A is not empty. Let's assume A is not empty. Now I can apply bell ordering because bell ordering says that whenever I have a non-empty subset of natural numbers, there is a minimum element. So let's just look at that minimum element. So let M be the smallest element of A. What do I know now? Well, I know that M is in this set A. So by definition, the GCD of Fm and Fm plus 1 should not be 1. Okay. So I know that GCD of Fm and Fm plus 1 is not 1. Let's give a name to this GCD. Let's call it D. Okay. So what does this mean? This means that D is a divisor of Fm. This is how I write divisor. So whenever I write something like this, it just means that Fm is a multiple of D. D is a divisor of Fm. Okay. And D is also a divisor of Fm plus 1. And remember, D is not 1, so I know that D is greater than 1. Okay. So what can I say here? I can use the formula for Fm plus 1. What do I know? I know that Fm plus 1 is Fm plus Fm minus 1. Okay. But here's the thing. D is a divisor of this side. And so the left side is equal to the right side. So D should be a divisor of the right side as well. But D is a divisor of Fm. So the only way that it can be a divisor of Fm plus Fm minus 1 is if D is also a divisor of Fm minus 1. So what I just proved here is that D is a divisor of Fm minus 1. Where's the contradiction here? The contradiction is that, well, now if I look at Fm minus 1 and Fm, their GCD is also not 1 because D divides Fm minus 1 and D divides Fm. So this tells me that M minus 1 is also in my set A. Right? But this is a contradiction because M was supposed to be the smallest element in the set A. So this contradiction shows that the set A has to be empty because it cannot have a smallest element, because whenever I have a smallest element, I get a contradiction. Okay. Now I could make the exact same argument, but I could also make it with infinite descent. Now the way I would make it with infinite descent is, instead of saying, well, let's look at the smallest element of A, I would just say, let's look at any element of A. Let M be any element of A, and I would then do the exact same thing, and I would say M minus 1 is also in A. So now I can make a sequence. I can say M is in A, so M minus 1 is in A, so M minus 2 is in A, and so on. This is an infinite sequence, and it's decreasing. We cannot have such a sequence. Okay. Great. And also, I mean, you can easily check this using induction as well. You can just use the inductive way of proving the same thing. Maybe I should do it. Let's actually do the exact same thing using induction, just so that you see 3 proofs of the same fact, 3 equivalent proofs. So here's the proof using induction. I just try the base case first. So my base case would be that I look at the first 2 elements. Well, this doesn't make much sense, but yeah, well, it does actually make sense. So GCD of 0 and 1 is 1. So it holds at the beginning, or I could also take 1 and 2 as my base case and say GCD of 1 and 1 is also 1. Okay, so my base case holds because GCD of F0, F1 and GCD of F1, F2 are both 1. Again, your choice which one you want to take as your base case. Now, how do I do the induction step? Suppose that GCD of Fn and Fn plus 1 is 1. So this is my assumption. What is the goal? What do I want to prove? The goal is to prove that GCD of Fn plus 1 and Fn plus 2 is also 1. Okay. Now I can do the exact same thing that I did here, and I can just do proof by contradiction. So I can say, suppose D is this GCD that I'm looking at. So GCD of the n plus first number and the n plus second number. And suppose that it's not 1. Okay. So what do I know? I know that D divides Fn plus 2, D divides Fn plus 1. These are all by definition. And I know that Fn plus 2 is Fn plus 1 plus Fn. So D divides Fn. And because the GCD of Fn and Fn plus 1 was 1, and D divides Fn plus 1 and D divides Fn, D has to be 1. Okay, so I could say the exact same thing using induction. It's just that depending on the problem, one of these 3 methods would just sound a little bit easier to do. It's just our human intuition. Otherwise, all of them are equivalent. Okay, let me do another problem. In 5, I want you to prove for every n that 1 cube plus 2 cube, so on, plus n cube is equal to 1 plus 2 all the way to n squared. Okay. So sum of the cubes of the numbers from 1 to n is equal to the square of the sum of the numbers from 1 to n. Okay, let's do this by induction. So I have my base case. And my base case is very easy. 1 cube is equal to 1 squared, yes. Now I want to do my induction step. So what is my induction step? I can assume that this holds. I can assume that this holds for n, and then I want to prove that it holds for n plus 1. So I can assume that the sum of I cube, I from 1 to n, is sum of I from 1 to n squared. Okay. And what I want to prove is the same thing, just that the sums go all the way to n plus 1. I from 1 to n plus 1 I cube is equal to the sum of I from 1 to n plus 1 I, all of it squared. Okay. So here's the thing. Let's just write this sum. So I have basically sum of I from 1 to n plus 1 of I cube. I can divide it in two parts. I can say, look at the first n terms first, and then look at the last term, right? But by induction hypothesis, I know what the sum of the first n terms are. It's just this. Okay, so this is just sum of I from 1 to n squared. Plus, I have n plus 1 cubed. Okay, so at this point, we have to use one of the problems that we solved last time, which was, what is the sum of all the numbers from 1 to n? 1 plus 2 plus 3 all the way to n. Yes, so it's just n times n plus 1 over 2. So here I can just say n times n plus 1 over 2, all of it squared, plus n plus 1 cubed. Okay. Now expand this. I'm too lazy to do it. Okay, whatever. It's n squared, n plus 1 squared over 4. I can then do this plus n plus 1 cube times 4. So I want to show that this is actually equal to this side. Sum of I from 1 to n plus 1 I, all of it squared. So let's expand this side as well. So this is what I started from the left-hand side, and this is what I got. So now let's start from the right-hand side, and let's see what we get. So sum of I from 1 to n plus 1, I, all of it squared, is going to be n plus 1 times n plus 2 over 2 squared. Okay. So this is n plus 1 squared times n plus 2 squared over 4. What I have to show now is that this thing, this numerator here, is equal to this thing. Okay. And just check it, it is equal. Again, I'm too lazy to do algebra, but these two are the same polynomials, they're equal. So we proved by induction that this always holds for every natural number. Okay. Let's do another one. So this is my problem 6. Suppose that I have a set of size n. So you can think of it as a set of natural numbers or anything. So let's A be a set of size n. I want to say that A has 2 to the power of n subsets. Okay. Then A has 2 to the power of n subsets. Now, again, this is an example of something that we will prove in this course using many different techniques, but at this point, I want to prove it using induction. Okay. so let's do induction on n, and let's look at our base case. My base case is when n is 0. So I have a set of size 0, which means it's the empty set. And how many subsets does it have? It has only one subset, which is the empty set, which is 2 to the power of 0. Okay, so the base case is easy to verify. Now let's say that I have a set of size n plus 1. And again, when I'm doing my induction step, I assume that this holds for n. So every set of size n is going to have 2 to the power of n subsets. Now I have a set of size n plus 1, and I want to show that it has 2 to the power of n plus 1 subsets. So I say let A be a set of size n plus 1. Okay, so I can write it like this. I can say that A is A1, A2 to AN plus 1. Let's say these are the elements. And I want to count the number of subsets of this set A. Okay, so I'm just going to look at the very last element, AN plus 1, and I'm going to say there are two cases. Either I'm going to include AN plus 1 in my subset, or I'm not going to include it. So let's count all the subsets that don't have this last element in them. Okay, so any subset B that is a subset of A such that B does not include AN plus 1 is also a subset of the first n elements, right? Is also a subset of A1 to AN. And vice versa. If I have a subset of A1 to AN, of course, it doesn't include AN. Okay. So the number of subsets that do not include the last element is exactly 2 to the power of n. Okay. But now what is the number of subsets that do include the last element? Well, I can take any of subsets that didn't include the last element, and I can just push the last element into it. Right? So the number of subsets that include the last element is equal to the number of subsets that do not include the last element. So I have 2 to the power of n subsets that don't have AN plus 1 in them, and I have 2 to the power of n subsets that do have AN plus 1 in them. So in total, I have 2 to the power of n plus 1 subsets. Okay. Let's do another problem, which would be interesting. Here's the thing. I say, let A be a finite set. And I want you to look at all subsets of A that have an even number of elements. And I want you to look at all subsets of A that have an odd number of elements. So let's say E be the set of all subsets of A such that the size of this subset is even. And similarly, let O be all the subsets that have an odd number of elements. Okay. Prove that these two have the same size. Prove that the size of E is equal to the size of O. So basically, if I give you any finite set A, and I tell you count the number of subsets that have an even size, and then I say count the number of subsets that have an odd size, these two counts are the same. Yes. Yes. Yes, you're right. Let A, which is non-empty, be a finite set, because the empty set itself doesn't satisfy this. Good catch. Okay. So now again, I can try to prove this using induction, or I can prove it in some other way. But let's do it by induction first, and then I'll do it by double counting next. So this is my proof by induction, so my base case. And by the way, what am I doing the induction on? What is my variable? I'm doing induction on the size of the set A. So let's assume that the size of this set is n. I'm doing induction on n. So my base case is when n is 1. So in this case, my set A contains only one element. And what are its subsets? I have the empty set, and I have A itself. Now, the empty set has an even number of elements because it has 0 elements, and A itself has an odd number of elements because it has 1 element. So I have one even subset and one odd subset, so this holds. For my base case, the number of even subsets and the number of odd subsets are the same. Okay. Now, let's do this. Let's do the induction step. And I'm just going to put the size of the set as a subscript. So I'm going to write an plus 1. So let an plus 1 be a set of size n plus 1. Okay. Because this is a set of size n plus 1, I can kick out one element, so I can find one subset that has only n elements. So let an be a subset of my set with n elements. Okay. What do I know about the subsets of an? By induction hypothesis, I know that the number of subsets of an with even size is equal to the number of subsets of an with odd size. Okay, so let's do this. Let me just use this E and O in the same way. So I'm not going to write the definition because I'm lazy. So let's say En is the set of even subsets of an. Okay, and I know that the size of En is equal to the size of On, where On is the set of odd subsets of an. Okay, so this is what I know by my hypothesis, and now I want to look at this new set an plus 1. Okay, again, I look at the last element. I look at the element that is in an plus 1, but was not in an before. Okay, so let's give it a name. Let's call it X. Let's say this is the only element that is in an plus 1, but was not in an. Okay, now I'm going to look at all the subsets of an plus 1, and I'm going to ask, do they include X or not? Okay, so here's the thing. I have subsets that do not include X without X. Okay, these are going to be exactly the subsets of an, just like in the previous problem. Okay, and let me write whether their size is odd or even, and let me write how many of them we have. So I have On subsets that don't have X and have odd size. And I have En subsets that don't have X and have even size. Okay. Now let's look at subsets with X, subsets that do include X. Okay. So I have X in my subset, and let's say the size of my subset is odd. If I kick out X, the size of my subset would become even, and then it would also become a subset of my first n elements, right? And vice versa. So here I can say that the number of odd subsets that include X is actually En, and the number of even subsets that include X is actually O. But again, by induction hypothesis, I know that the size of En is equal to the size of On. So these numbers are all equal. I have On plus En on top. I have En plus On on the bottom. They're all okay. But interesting point, I'm not even using this equality. Because in any case, I have On plus En and En plus On. Let's do another problem. So this problem is one of the first counting problems that we're going to see in this course. So let's say we have a class of n students. Suppose we have a class of n students. And let's call this C. And let's say that I want to give some of these students A. So let A be a subset of C. And basically, and then I want to give some other students A plus. And A plus is a subset of A. Okay. So A plus is a subset of A, is a subset of C. And my question is, in how many different ways can I do this? Okay, so in how many ways can I choose these two sets, A plus and A, such that one of them is a subset of the other? How many ways can we choose A plus, subset of A, subset of C? Now, this is a typical counting problem that we will see in this course, and it's actually a very easy problem. But right now, the problem is that I only know mathematical induction. And because I only know mathematical induction, I have to somehow first guess the answer and then try to prove the answer using induction. Okay, so guess the answer. Try it for like small values of n and give me a guess. So this happens all the time with induction problems. You usually don't get the answer so that you can just prove it. You're just asked, what is the number of ways you can do this? You have to guess, and then you have to prove your guess by induction. So let's say, first case, if n is 0, what does this mean? This means that the class is empty. So the set of people who are getting A plus and the set of people who are getting A has to be empty as well. So A plus must be equal to A, must be equal to empty. So how many choices do I have? I have only one choice. The only choice is to choose the empty set for both A and A plus. Okay, so one choice. Now let's say n is 1. So in C, let's say I have only one student. I'm going to call that 1. Now, what can I do with this one student? I can either not give them an A, or give them an A but not an A plus, or I can give them an A plus. So I have 3 choices. Okay, so I have 3 choices. Now let's say n is 2. I now have 2 students. But for each one of these 2 students, I have one of the 3 choices. Right? And whatever I choose for student 1 is completely independent of what I choose for student 2. So I actually have 9 choices now. Okay. And generally, I guess that if I have n students and my C is like 1, 2 to n, I would have 3 to the power of n choices. This is my guess. Okay. Now I have to prove this guess. And I'm going to use induction to prove it. Now, the base case of the induction is pretty easy. I've already done the base case here. So this is my induction step. I say that suppose that for a class of n students, I have 3 to the power of n ways. So for a class with n students, we have 3 to the power of n ways. Now let's say that I have a class with n plus 1 students. So let's say my class is 1, 2, 3 to n plus 1. So I said, let's just look at the first n students and let's figure out how I want to divide them. And I know that I have 3 to the power of n ways of doing that. Okay, so for the first n students, I have 3 to the power of n ways of deciding which ones get A and which ones get A. Now let's look at the very last student, student n plus 1. I have 3 ways of choosing what happens to student n plus 1. And I can combine any choice that I have for this last student with any combination of choices that I had for the previous students, because they're completely independent of each other. Right? So I have 3 to the power of n ways to decide the fate of the first n students times 3 ways of deciding the fate of the last student. So this is going to give me 3 to the power of n plus 1. Now, let's do some more interesting stuff. This is problem 8. Let's do problem 9. So we want to play a game. And this is a 2-player game. Here are the rules. I write 2 numbers on the board. So let's say 12 and 20. And we have 2 players, they take turns. Whenever it's your turn, you can choose one of the numbers and you can decrease it. You have to keep it a natural number, but you have to decrease it. Okay. And the player who cannot make a move will lose. So I want someone to play this game with me right now. Yes. You cannot reduce both of them. You can reduce only one of them. Okay. So we'll do this. Okay, now it's my turn. I can again reduce one of the numbers. This is what I do. Okay. I think everyone saw what's happening here. So now from this point onwards, whatever you do, I'm going to copy it. So if you say I reduce this one to 10, I'll say, okay, I'll reduce this one to 10 as well. So eventually we'll get to a point where you will have to make one of the numbers 0, and I get to make the second number 0, and I get. Okay. Now, I want you to consider this game. Now, the first thing I want you to prove is that this game always terminates. It's impossible to play this game for an infinite number of steps. Now, that's pretty easy to prove. Why? Because just look at the sum of the 2 numbers that I'm writing. The sum of the 2 numbers is always going down. So I can just make a sequence. I can write the sum of all the numbers at the very beginning, the sum of all the numbers after the first move, after the second move, and so on. And this is going down. And I cannot have an infinite decreasing sequence of natural numbers. So this cannot continue forever. At some point, the game has to end. But I want to prove something nicer. I want to say, suppose that both players are infinitely smart and they make no mistakes at all. Okay, so this is actually called a game of NIM, and it's a game of NIM with 2 heaps. So we call this a game of NIM, and we will analyze this game later on in this course in a more general case. But let's consider a game of NIM with 2 heaps, which basically means I have 2 numbers, and every time the player can decide to reduce one of the numbers. game of NIM with two numbers. Let's call these numbers A and B. Okay. And let's assume that both players are infinitely smart and they never make any mistakes. Okay. Let's assume both players are smart. Okay. This is what I want you to prove. I want you to prove that the winner depends on whether A is equal to B. Okay. So I want you to prove that, well, of course, initially A and B are also greater than or equal to 0. I want you to prove that if A is equal to B, then player 2 wins, and vice versa. And if A is not equal to B, then player 1 wins.
Copy the other players.
Yes, so that's the idea that we have. But the question is, how do we prove that it actually works? And can we do it by induction? It's probably easier to do it by infinite descent. But can you do it by induction?
First, prove the first case inducts on A equals to 1 from N. And then if we have the second case, the first player just negates the first case.
Okay, so basically, let's do induction on A, right? So first of all, the order of the numbers don't matter, right? So I can always assume that B is greater than or equal to A. I always call my bigger number B, okay? So let's do induction on A. Okay, and right now, I want to prove this first one. I don't care about the second part, that if they're not equal, player 1 wins. Let's just prove that if the numbers are equal and they're both A, then player 2 wins. And I'm doing induction on the number. Okay. So what is my base case? My base case is that I have 0. Right. So I have 0, 0. Now, in this case, player 1 cannot move. So player 2 wins by default. Right. So in this case, player 2 wins. I'm happy with my base case. Okay. Now, let's do the induction step. By the way, in the exam, you have to actually write everything that I'm saying. I don't write everything, but you have to explain what you're doing. So in the induction step, let's say that I have A plus 1, A plus 1. Okay. Now, what is my induction hypothesis? My induction hypothesis is that if I start the game at AA, player 2 wins. But I'm starting the game at A plus 1, A plus 1. Now, maybe player 1 is not really doing well and changes one of these A plus 1s to A. Okay. If player 1 changes one of these to A, then player 2 can change the other one to A. And then we're back to the case AA. And by induction hypothesis, I know that player 2 wins here. But what if player 1 decreases this much more? What if, let's say, A plus 1 was 10, I had 10, 10, and player 1 goes to 5. Now, in our intuition, it was that, well, player 2 will change the other number to 5 as well. But that's not my induction hypothesis anymore, right? So if I want to write my induction step formally, what is my induction step? It's that assuming player 2 wins if I start at AA, prove that player 2 wins if I start at A plus 1, A plus 1. And I don't really have that here. I started with A plus 1, A plus 1, but then player 1 reduced one of these numbers even below it. So I need a new type of induction here. And this is what we call strong induction. And it's actually equivalent to the normal induction that we've seen so far. So this is strong induction. Now, the situation is very similar to before. It's that I have some property, and I want to prove that this property holds for all the natural numbers. Okay, so I want to prove that some property P holds for all natural numbers. I want to prove that for every natural number n, P of n holds. Okay. Now, what I did in normal induction was that I said, well, P of 0 holds, and I also proved that whenever P of I holds, P of I plus 1 holds, right? But here, I'm going to change it a little bit. I'm going to say, prove two things. First, prove that P of 0 holds. So this is my base case. And again, just like before, if I just wanted to prove it for n greater than or equal to 1, I would change my base case to P of 1. Okay. And then the second thing is this. I say prove that for every n, if P of all the smaller numbers hold, then P of n holds as well. So for every natural number n, if I have P of 0 and P of 1, and so on to P of n minus 1, then this implies P of n. Okay. This is why we call it strong induction, because I'm making a stronger assumption here. Previously, in normal induction, I just had to say for every n, if P of n minus 1 holds, then P of n holds. But now I'm saying for every n, if all the previous P values hold, then P of n. And by the way, of course, I get to choose how to write this. I could also say that this goes all the way to n, and it should imply P of n plus 1. This is the same thing. Okay. Now, I claim that strong induction is equivalent to induction. Now, if I prove something using induction, I can, of course, also prove it using strong induction, because strong induction is just giving me more assumptions here. So whatever proof I had using induction also works using strong induction. But you have to prove the other side. Suppose that I've proven something using strong induction, show that I can also prove it using normal induction. That's in your problem set for this week. But it's actually very easy. It's much easier than you think. Okay, so now the intuition is obvious, right? So basically, the idea was that when I was doing induction, I said that this property holds for 0. And then whenever it holds for n, it also holds for n plus 1. So it holds for 0, therefore it holds for 1, therefore it holds for 2, and so on. But now I'm saying that I prove that my property holds for 0. And whenever it holds for 0, it will also hold for 1. Whenever it holds for 0 and 1, it will also hold for 2. Whenever it holds for 0 and 1 and 2, it will also hold for 3. So I keep all the things that I have proven so far as assumptions. That's the idea in this strong induction. Okay, so let's solve this problem 9 using strong induction now. So we're going back, and I'm saying, let's do strong induction on A. So my base case is when A is 0. And again, remember what I want to prove is only the first part. I want to prove that if A is equal to B, then player 2 wins. So what I have, the numbers that I have are AA. Okay. My base case, when n is 0, 0, 0, player 2 wins. We check that, we're happy with that. Now let's do induction step. Let's say, I'm going to erase this one because I'm not going to use normal induction. I'm going to use strong induction. Let's say that I have n plus 1, n plus 1. And what is my assumption? My assumption is that if the game gets to 0, 0, player 2 wins. If the game gets to 1, 1, player 2 wins. If the game gets to 2, 2, player 2 wins. If the game gets to n, n, player 2 wins. So I have all of those things as assumption, right? So my assumption here is that basically for every I that is less than or equal to n plus 1, player 2 wins II. Okay. But now the case that I find myself in is n plus 1, n plus 1. So player 1 has to make the first move. Player 1 has to reduce one of these numbers. Takes one of these n plus 1s, it doesn't matter which one, and reduces it, let's say, to I. Right? And I is less than or equal to n plus 1. So player 2 just copies the same move, takes the other n plus 1 and turns it to I. And now I'm at state II, and by the strong induction assumption, I know that for this II, player 2 wins. So no matter what player 1 did, I had a strategy for player 2 to win, so player 2 always wins. Okay. Now, I've only proven this first part. I've proven that if the two numbers are equal, then player 2 wins. But now the second part is really easy. If the numbers are not equal, player 1 just makes them equal, and now basically the role of player 1 and player 2 has swapped, right? And then player 1 wins. So the second part is quite easy to prove. Okay. I could say the same proof using infinite descent instead of using induction. So this is the idea that you had here, which is like, well, I just give a strategy for player 2, and I prove that this strategy will always win in this case. So the strategy is just a copycat strategy. It's that, well, I have two numbers, they're equal. Player 1 changes one of the numbers, reduces one of the numbers. I'll just copy the same move. I make the other number equal to this, and I keep doing this. Okay. Now I have to prove that if player 2 just follows this strategy, player 2 always wins. Now, how can I prove that? Well, by infinite descent, I've already argued that the game will end. So the game cannot go on forever, right? But when does the game end? The only case that this game can end is if we reach 0-0. But who's the player that is actually reaching 0-0? So every time that player 1 is moving, they're changing the numbers so that they're not equal. Every time that player 2 is moving, they're making the numbers equal. So the player that reaches 0-0 is player 2. So the player who cannot move is player 1. So you see, we could actually use infinite descent to prove the same thing.